We'll start our review of vector addition by defining what a vector is. A vector is a quantity that has both a magnitude and a direction. It can be represented graphically by an arrow that is drawn so that it points in the direction of the vector quantity and has a length that's proportional to the magnitude of that vector quantity. For example, map directions are commonly represented as vectors. The direction 10 meters north would be represented by an upward pointing arrow, while the direction 10 meters to the east would be represented by an arrow pointing to the right that has the same length as the arrow pointing upwards for 10 meters north. Note that these two directions would get you to very different places if you started at the same location. So they are very different quantities, even though they have the same length. They have a different direction, and that makes them distinctly different vectors. 14 meters northeast would be represented by a diagonal arrow pointing up and to the right. That would be 1.4 times as long as the length of the 10-meter arrow. In physics, we prefer to represent the direction with an angle. By convention, the angle is 0 degrees when pointing straight to the right. Angles are then represented as being positive as you move counterclockwise around the circle. So 90 degrees would point straight up, 180 straight to the left, 270 straight down, and 360 would bring you right back to straight to the right. And so in physics nomenclature, these map directions would be denoted by a magnitude and an angle. Next, let's consider how we can add two vectors together using a graphical method. Vector addition must account for both the direction and the magnitude of the vectors to be summed. So if we have two vectors that we wish to add together, we would sum these two vectors graphically by translating the second arrow so that its tail sits at the head of the first arrow. By translate, we mean to slide it without rotating it. If we do this, then the vector sum is then represented by the resultant arrow, r, which points from the tail of the first arrow to the head of the second arrow. Similarly, we can handle vector subtraction as a special case of vector addition. Recall that subtraction can be written as a minus b is the same as a plus the negative of b. This we do in algebra all the time. The same is true for vector addition. To utilize this method, we need to understand what it means to have a negative vector. The inverse of a vector, or a negative vector, has the same magnitude as the original vector, but points in the opposite direction. So if we want to subtract vector b from vector a, what we do is we graphically invert the vector by flipping it by 180 degrees. We can then add the inverted vector to the first vector using the same head to tail graphical method to give us a resultant vector that goes from the tail of the first to the head of the second vector. To utilize the vector component method of vector addition, we first need to break down the individual vectors into their components. So consider a vector A oriented at some angle theta relative to the horizontal. Remember, positive angles are taken to be counterclockwise from the positive x-axis. The x component of the vector A is given by the cosine formula. Ax is equal to the magnitude of A times cosine of theta. The y component, ay, of the vector A is given by the sine formula. Ay is equal to magnitude of A times the sine of the angle. As an example, if the vector A had a magnitude of 6 meters in length and was at an angle of 60 degrees with respect to the horizontal, then our formula would give us that the x component of the vector A is 6 meters times cosine of 60, which gives us 3 meters. Similarly, ay, the y component of the vector A, is found from multiplying 6 meters times the sine of 60 degrees. Sine of 60 degrees is roughly 0.866, which gives us a final answer of 5.2 meters for the y component. Let's consider two vectors, vector A and vector B, whose angles are given by theta A and theta B relative to the horizontal, and whose magnitudes are given by the absolute value of A and the absolute value of B vector. Let's calculate the vector sum. To get the resultant vector, we can, of course, use the graphical head-to-tail method we described previously, or we can use the vector component method. So let's take a closer look at this vector component method. To use the vector component method to add vector A to vector B, we first start by finding the x and y components of both the A vector and the B vector using our sine and cosine relationships. So for the A vector, we get the x and y components from the cosine and sine formulas. Similarly, for the B vector, we get the x component and y component of the B vector using its magnitude and its angle. And then, to find the components of the resultant vector, we simply sum the x components of A and B to obtain the x component of the resultant vector. Similarly, we can add the y components of A and B to obtain the y component of the resultant vector. This, of course, forms a right triangle with Rx and Ry being the sides of the triangle, and the resultant vector itself lying along the hypotenuse. And so we can use Pythagorean's theorem to find the magnitude of the resultant vector. Remember that the tangent of the angle is equal to the opposite over the adjacent, or in this case, Ry over Rx. And so we can find the angle by taking the inverse formula, or the arctangent of Ry over Rx, to give us the value of the angle that we're looking for, specifically the angle that the vector r makes with respect to the horizontal axis. Let's work through an example real quick. If A has a length of 6 meters and makes an angle of 60 degrees above the horizontal, while B has a length of 10 meters at an angle of 15 degrees above the horizontal, then let's calculate the result of adding A plus B using our vector component method. First, we find the x component of the A vector by using the cosine formula. Plugging in the numbers, we get 3 meters. Next, we can use the sine formula to find the y component of the A vector. Again, when we plug in the numbers, we get 5.2 meters. We do the same thing for the B vector. Plugging in the numbers, we get Bx is equal to 9.66 meters, whereas By, using the sine formula, gives us 2.59 meters. Now that we have the x and y components for both vectors, we find the x component of the resultant vector by adding just the x components of the two vectors. Plugging in our results, we get 3 meters plus 9.66 meters, gives us 12.66 meters for Rx. Similarly for Ry, we sum the y components of A and B to give us 7.79 meters. Our next step is to use Pythagorean's theorem to calculate the magnitude of the resultant vector. Plugging in our numbers, we get a final answer of 14.86 meters. And finally, we use our arctangent formula to figure out the angle that the resultant vector makes with respect to the horizontal axis. Plugging in our numbers, we get an answer of 31.6 degrees.